To start, or okay, good. Go or yeah. Okay. All right. Well, I'll get started here. Thanks for showing up. Thanks for sticking around to the last session to show up for this. My name's Taylor Patterson, and I'm a research associate at Oak Ridge National Lab, which is a U.S. Department of Energy research facility. I'm a developer on an Eclipse project there, and I'm here today to share with you some work that we've done in order to get scientific visualizations into our Eclipse project, and how we've integrated another large open source project in order to achieve this. Ultimately, as you'll see, we end up with 3D visualizations inside an Eclipse editor, and that's something that I always think is kind of cool to see. So first, to look at where we're headed over the next half hour or so. I'll start with an introduction to the Eclipse project in general, which is Eclipse ICE. Then move on to discussing the visualization toolkit that we integrated into our project. I'll test fate with a live demo, which some of my colleagues have told me doesn't always go over so well. And then come back to the slides and kind of dig into the details of the features available in our product, as well as get into the implementation details. So first, what is Eclipse ICE? Eclipse ICE is the integrated computational environment. If you've attended a talk by one of my colleagues at either one of the last 2 EclipseCon North America events or at EclipseCon France in June, you've probably seen this project presented under the name NICE. And although the project hasn't changed, the Oak Ridge National Lab joined the Eclipse Foundation earlier this year, and we became an Eclipse project. And as part of that transition, we took the opportunity to change our name to reflect more of what we do. NICE was initially developed to serve nuclear reactor simulations, but as the project has matured and grown, we now serve tools in the fields of virtual battery simulation, climate modeling, material science applications. So in our transition to an Eclipse project, we took that opportunity to do a little bit of rebranding, drop the leading N off our name, and reflect that we do more than nuclear engineering. Although in the Eclipse community, we prefer to be called ICE. The nuclear energy community doesn't necessarily enjoy that. So we didn't really change the name. We just added a name, and for you guys, we're ICE, and for the nuclear energy people, we're NICE. I explained the name, but now what does it actually do? ICE was created to serve what we have termed the standard model of scientific computing. And all problems in scientific computing, we say, require the user to complete 4 tasks. First, the user has to define their input and define their problem. Oftentimes, this requires the user to create a file or collection of files that can be cryptic in nature, not well understood by a lot of people. It reflects something like a dead language, like the Mayan that I have up here, where there aren't a lot of standards for it. It's not well understood. The same idea can be expressed by several different arrangements of characters. That it's very non-standard and difficult to understand. After essentially conquering the task of defining the input, the user has to then launch that simulation run, oftentimes requiring the use of leadership class computers such as Titan at Oak Ridge National Lab. Just a quick poll of the room. Has anybody used a machine like Titan, something that has roughly 300,000 cores, operates in petaflops? Just, yeah. I sit less than half a kilometer away from that, and I've never used it. So the number of people that are used to regularly executing jobs on machines like this is very limited. After executing a job, the user is then presented with usually binary output that can be up in the scale of petabytes of data, not in a format that's easy for them to understand or interpret or gain anything useful from. Like I said, it's usually binary output. I've had this slide up for the past minute and a half, and probably no one has taken the time to realize that that image is the binary representation of the English word binary. So like it's difficult to understand and not easily interpret. You can't analyze it easily. And even with those petabytes of data, then you need to somewhere archive that and keep it. For super users, these tasks are simple. Open up a shell and run the commands that they need to. But for new users and novice users, these tasks quickly become overwhelming. And the thing that separates super users apart from new users is simply experience. And a super user of one simulation code is not necessarily a super user of another. So by switching between codes, oftentimes those people that we consider super users become new and novice users by just switching the problem that they're doing. And to address this, we say, well, why not have a software application manage this for the user and take care of everything? And that's where ICE steps in sort of to the scientific computing equation, that ICE provides the single user interface for users to complete all 4 of these tasks in a neat and organized manner. For the remainder of this talk, I'm going to focus on just one of these tasks, which is analyzing output. And I'm going to focus on this task in one very specific way, through the use of 2D and 3D visualizations. In order to achieve this task, we've integrated the Visit visualization toolkit into part of ICE that provides our file management and image rendering technology so that we can provide visualizations to the user. Well, now I introduced Visit, but I have a responsibility to tell you what Visit is. Visit is a open source parallel tool for creating visualizations of data defined on 2D and 3D meshes. It was developed at other laboratories within the United States Department of Energy Research Complex. And it was originally developed to visualize the output of terascale and has since moved to petascale simulations. It allows the user to create visualizations like the ones that I've shown here, where on the bottom there is an elevation map of Europe, and on the top is a single frame from an animation it's an explosion in a bunker, and they've also included a little figurine type in there to demonstrate the size of the blaze. And as I mentioned, this was originally developed for supercomputers, but has proved useful on desktop machines as well. It's very versatile in the file formats that it reads. Visit's a very powerful tool and something that users should want to work with. But it exists as its own application, so why would we want to include it in ICE? I mean, it's already available to the user. Doing modern HPC simulation requires 3D visualization in order to effectively analyze the abundance of output. And ICE, as I mentioned, seeks to be a complete end-to-end tool for completing all of the scientific computing tasks. So including Visit in ICE just simply becomes necessary. The user needs a tool like this, and it needs to be in ICE. Including it in ICE also provides, as I mentioned before, a familiar UI for all steps of the process, as well as, in some instances, we have users of other parts of ICE that were already leaving ICE in order to do their analysis in Visit. So by providing it as in a single application, we then give them the potential to hopefully be more productive. I've given the intro of ICE and Visit. Let's take a look at it with a live demo first, and then dig back into the slides to discuss the details. When ICE starts up, the user is presented with the default ICE perspective. In order to better address the needs of our integration with Visit, we've introduced what we've called the visualization perspective. And then, so after opening the visualization perspective, the user needs to create a connection to Visit, which is done through this Launch Visit button at the top. This presents the user with a dialog that allows the user to connect to Visit in three different ways. The user can launch Visit either on the local machine by just simply providing a path to where that's, excuse me. The user can simply provide a path to where visit is on the local machine. Optionally, they can provide a port for visit to serve data to, and a password. These two options will be more clear when I discuss the other connection options later. There's an option for the user to launch on a remote machine as well as connect, and I'll discuss these when I get back to the slide. For the demo, I'll just use a local connection, and in fact, I already created one before I started, so we'll just cancel out of this demo and use that. After a connection to visit is created, the center area of the visualization perspective is filled with this visit editor. And in order to start visualizing things and creating plots, we have to first open a visualization file, which is done over in the visualization file viewer. By clicking on that, we're presented with a dialog. Let's see here, we'll just grab some data from a virtual battery simulation. As I showed there, when I just clicked on it, I was presented with the option to select a file from the local file system. I need a file that's also running, or that's also available where visit is running. So we've provided options to add remote files to this dialog if you're using a remote connection to visit. With a selection made in the visualization file viewer, the user can add plots over in the visit plot viewer. And by selecting the Add Plot button, we're presented with a dialog that allows the user to select any subset of the plots that are available in that file. For this demo, I'll just grab all of the scalar values. Those selections then populate the visit file viewer, and then making a selection in the visit plot viewer renders up in the visit editor. The user can then interact with this by clicking and dragging for rotations and using the wheel to zoom. One additional feature that I want to highlight here in the demo and then discuss in more detail later is that Visit has a rich and mature Python API, and as a sort of a hot fix or a quick way to access this, we've just created a dialog that allows the user to input commands from the Visit Python manual. So I'll just execute a simple one here, and that's immediately reflected in the plot that the user has previously created. So we'll get back to this. We'll get back to the slides here and then dig into the details. So as I mentioned, the three connection options. The remote connection is similar to the local connection. You need a path to where visit resides, provide the host name for the remote machine where visit's installed. Optionally, provide the port and password that are useful in the connect to visit option that I'll move on to next, as well as the option to use an out-of-network gateway in situations where that becomes necessary. Using a remote launch allows the user to launch visit on a separate machine and do all of their rendering work, or I guess essentially outsource all of their rendering work and all of the visit computations to a separate machine, conserve hardware on your local machine where ICE is running. The connect to visit option is the third option. As I mentioned with the port and password, if a user launches visit somewhere, keeps track of the host name, port, and password, they can distribute that to others, and they could enter that here and connect to the same visit client. This would allow the users to do essentially collaborative analysis. Two users separated by any distance, each with their own instance of ICE running, can connect to the same visit client and view exactly the same data, interact with it with the mouse clicks and drags, analyze that data, and have it reflect on both machines at the same time. But it's not just limited to multiple users connecting to the same thing. Visit provides support for up to 16 unique IDs on a single instance. So a collection of users could essentially connect to the same machine running Visit, and each provide a unique user ID between 1 and 16, and individually do their own visualizations. This allows for, say, you could install Visit in a render farm or a dedicated cluster, and all of your colleagues within within a research team could use the same visit instance simultaneously. The entire system is made up of essentially 3 components. The first component being the ICE client, which is the user front end that collects data such as the connection parameters, user selections of plots and files, mouse interactions. These are then collected by a visit Java client that acts as an interface to the visit application itself. The connection between the visit Java client and the visit application is made through an SSH connection that's managed by leveraging the Java Secure Shell API. Communication between the Java client and the visit application is then executed by passing JSON objects between the two on the visit Java client side. These JSON objects are encoded and decoded using Google's JSON library. If you want to start using this, you essentially need 2 executables. The Eclipse ICE executable provides both the Eclipse ICE application and the visit Java client, and then which are available on our website, which I'll provide at the end. And the visit executable is available through Visit, but if you want the latest and greatest, contact us. If you would like to start wrenching on this stuff yourself, our Eclipse ICE repository is currently hosted on SourceForge, but quickly moving to Git. The Visit Java client is already on a GitHub project, and Visit distributes their executables as a download through their website. But again, if you want the latest version of the trunk, come through us and we'll help you out. So let's pull back the curtain just a little bit on the Eclipse ICE part of this. As I mentioned in the demo, we created a dedicated perspective for this that we named the visualization perspective. And digging into the visualization perspective a little bit further, let's take a look at the Eclipse technology that's at work here. The visualization perspective is made up of essentially 3 key views. And we'll take a look at each one of these, starting with the viewers on each of the sides. So the visualization file viewer on the right here receives its data through user selections in the file dialog. Both these views are viewpart subclasses, just containing standard JFace tree viewers. And selections made in the visualization file viewer can then be used to populate the visit plot viewer through the add plot action that I demonstrated. The checked tree selection dialog subclass is populated by visit. So a connection to visit parses the file selection and creates this list, or creates essentially a database of available plots that the user can select with, and then selections from the dialog get reflected in the visit plot viewer. Selections in the plot viewer show up in the middle in the visit editor that fills the middle section of the visualization perspective. And this editor is a editor part subclass that's filled by an SWT canvas subclass. The SWT canvas subclass displays an SWT image that is initialized through a byte array input stream. And we've then applied listeners to this canvas in order to manage the mouse methods. And the mouse listeners then pass that on to the visit application. I demoed the Python interface as well. As I mentioned, Visit has a very rich Python API, and in order to expose that to the user immediately, we kind of threw in this hotfix to provide this as a dialog. This becomes useful if the user prepares a script. They have a frequently used analysis tool chain or analysis workflow that they often go through. Say, for example, a user runs several instances of the same simulation with different input parameters and then has the same output from all of them but needs to analyze them for differences. Well, they could script up the way that they'd like to analyze that, perhaps apply a certain color map, orient the camera in a certain way, and slice it to just a subset of that data. They script that up in Python, and click on the load from file option in this dialog, they can then execute that script on all of their output and be presented with the same image, or at least what would be the equivalent images from each simulation run. One obvious thing from this is that, as Eclipse developers, we're probably thinking, well, why is this in a dialog? This is temporary. This is moving to an org.eclipse.ui console. We just haven't gotten it there yet. And that pretty much wraps up the current state. So where is this work headed, both on this project and as Eclipse ICE as a whole? Well, as I mentioned, we want to get more capabilities directly into the workbench rather than using that Python API. For example, we currently have a time slider available for time-varying data contained in the same plot or same file, and that's just sort of sitting in the trunk right now waiting to be merged. ICE as a whole is currently built on Eclipse 4, but we're currently using Eclipse 3 views on the compatibility layer. We're working to move entirely to Eclipse 4. We're also trying to get more involved in the community through the science working group and sort of try to bring in additional tools that have been developed within the working group to add further capabilities to ICE, as well as gaining users by communicating with the science working group. We've started a good dialogue with the people at Diamond in the UK and have some work there for some exchange of tools there and provide some of our capabilities to them and get some of their capabilities in our project. I guess targeting EclipseCon North America, we'd like to get something in there in order to further discuss the collaborative analysis capabilities of this. We have some work going on in order to get this visit tool to get the visit tool in ICE into virtual reality environments. So hopefully by March we'll have something to demo as far as Eclipse in a cave. And with that, I'd like to encourage you then to check out our project. We have a number of YouTube videos available. Check out our SourceForge page. For now, migration to Git is going to begin next week, so that we'll be on an org.eclipse Git repo. And with that, I'll turn it over to you and open it up for questions. Yes, sir.
Yeah, in the past I worked on a similar project where we tried to visualize simulation data into the Xenius visualization toolkit. And we discovered quite a lot that we have difficulties on user interaction and in particular navigating through simulation data. So we discovered that just mouse control is not enough. And we face difficulties in particular with this combination of equal that we could not get tools like space mouse or something like that running. Did you face similar problems, or do you actually have solutions to that?
Could you repeat the end of it? I didn't quite catch what the...
Sorry?
Could you repeat that? I didn't quite catch all of the question at the end.
It's like that we have issues to have good user interaction with
Yeah.
the simulation data in this place. So do you encounter the same trouble, or do you also have many solutions already to include more fancy interaction tools like space mouse?
Right. Well, we certainly have a lot of work ahead. And yeah, as you mentioned, that the UI can certainly become cluttered or difficult. Getting, say, for example, visits capabilities for slicing data is certainly going to be a challenge for us to find out an efficient way to address that on the user side. Do you have any more specific challenges that you ran into? We should probably talk afterwards, because I'd like to hear where you ran into problem, because you were using VTK then, right?
Yeah.
Okay. Yeah. So come talk to me afterwards, that we can kind of see where we're headed and kind of prepare for that, maybe.
Yep.
Thank you. Oh, sure. Yeah, right now the raw image, and it's the full image, gets encoded and passed. In order for speed, we're looking at solutions for just sending image differences, which we certainly need to address in order to, like I said, address that speed issue. But right now it's full images encoded in JSON, passed back and forth, which, at least for what I demoed, doesn't look too bad. But certainly when we get into the capabilities of Visit, which Visit has set and broken its own record several times for the largest file ever rendered on a supercomputer, starting with trillions of elements in a mesh up to tens of trillions of elements. So if we start working with stuff like that, passing full images is going to become something that is just not manageable. So we're looking for ways to better address passing differences rather than full images. Is there anything else? All right, if not, please come and talk to me if you have any other questions that might come up. I'd like to encourage you, well, I'd like to thank you for showing up and encourage you to include feedback for me and let me know how we can improve this. But thanks for coming.